I'm going to remind you what we were doing. So last time we started talking about sufficiency. This is a general classical idea, and it's a way of basically summarizing the information in the observations as far as estimation of like the parameters of the model goes. So if we start with a model, statistical model or decision theoretic model, which is a parametric family of distributions, we will have a sufficient statistic if when I condition the data on this statistic, the distribution, the conditional distribution does not depend on theta. So this captures the idea that if I observe t, given t, what is in x does not have anything to do with theta anymore. And so I can just discard, or in other words, I can simulate. So there's this kind of probability distribution. So this is formalizing the idea that when I condition x on t, I'm looking really at a probability distribution. If you read Inner, it goes into details of how to define actually these conditional expectations properly in the measured theoretic sense. And you're dealing with the so-called regular conditional expectations. So there is this really probability measure for every t that gives it the conditional distribution. And so this is going to be known to the statistician because it's a property of the family, not dependent on theta. So once I observe t, I can draw from this distribution and produces an x, which is statistically equivalent to t. So we can simulate the original data back. This gives another way of, like, sort of equivalent way of thinking about sufficiency. So it's a statistic such that once I have it, I can simulate my original data statistically, like something that has the same distribution as the original data. So and then we went on to sort of discuss or see how this is actually implemented in practice. So this is the coin tossing example. We observe a binary sequence of coin tosses encoded as 0, 1. And the claim is that the sum of these xi's, basically to count how many ones there are, this is sufficient for estimating theta, which is the probability of observing a 1. And so we wrote down the conditional, not the conditional, the probability mass function for this sequence, which factorizes. And so simplifies to, as we use this compact notation or like compact variable, unique PMF or density, and then we get this quantity. Like as a nice compact form for the PMF, where T of X is just the summation of the xi's. So again, I distinguish between this capital X, which is the random sequence, and this little x, which is the realization. And we also, like, with some abuse of notation, we both write t for the statistic and also write t for the functional form. So you can think of t of x as t of little x really is just summation of xi. So if you give me a sequence, I just sum them. So for example, t of this would be 4, right? So we also look at it as a function. So really the statistic t is this function applied to random x. So next we looked at the joint. So in order to compute the conditional probability, I can use everything is discrete, so I can use like regular basic 101 probability. So probability of A conditional on B is probability of A intersect B divided by probability of B. So probability of A intersect B is the joint, a sort of joint distribution, joint PMF of X and T. And this, we argued that this turns out to be like this. So this requires a bit of thinking because these two are dependent, so this is basically T of capital X. And if I require that XT equal to little x, and T of capital XT equal to little t, so this can only happen if when I apply t to little x, it matches t. Okay, so the same, I have a sequence, the count is t. It only has 0 probability if the sequence has really that count. So if, for example, t turns out if the sequence is this, and little t is 5, this can't happen, right? So what it's saying is that the indicator is doing this. So if t of little x is equal to t, then we are good. In that case, this is vacuous because it just says that the sum of the sequence is 4. We know that it should be 4 in this condition. So then in that case, this is just going to be just p of x. Otherwise, it's just 0. And then once I have this, I can plug this formula in. And because I know t of x is equal to little t, I can just replace it with little t. Okay, so this sort of obvious, but it's like the trick. Because under this t is no longer dependent on x or anything else. This is just something that is fixed. And then once you look at this part only depends on that t, not on this x anymore. And then in order to compute the marginal distribution, which is p of x equal to x, because I want to divide by that, I can just sum, sorry, I want to divide by p of t equal to t, I just sum over x. So I hope everyone knows that this is obvious, sort of, that in order to get this, I can just, I have the joint, I marginalize x, sum over x. X varies in all of the sequences of length and binary sequences, and that this sum passes through this part because this doesn't depend on x. So you're effectively just summing over this part. And when you sum over this part, if you think a little bit about it, it's just, this is just the number of sequences or binary sequences or 0, 1 sequences of length n with t1s. It's a very classical counting problem. I have n positions and t of them are 1s. So it's like n choose t ways I can rearrange these 1s, basically. Just pick the location of the 1s and the rest have to be 0. So that gives me this thing is just n choose 2. Sorry, n choose t. We end up with this marginal distribution, which you already probably knew from basic probability. This is just saying that what is this distribution? Sorry? Binomial. So it's like just binomial n and t. So we just proved that if you have a bunch of Bernoulli variables, IID, and if you sum them, the sum has the binomial distribution. You probably could have just wrote this down, but once you have that, then this is easy. Then I divide the joint by this marginal. As you can see, this part cancels out nicely. This piece and this piece, or say this piece, cancel out. And I just get that indicator, this part, divided by this, okay? And we look at this and we see there's no theta in it. And so we've proven that P is sufficient, okay? Fairly a straightforward argument. The only tricky part is actually calculating this joint. In the discrete case, it's sort of easy. In the continuous case, it's not easy. So that's where we wave our hands around, as you'll see. Because it wouldn't be a regular kind of, usually it's a singular probability distributions. Even if x has densities with respect to the Lebesgue measure, once you try to compute this probability, it doesn't have a density anymore because of the dependence of x and t. So you're forcing a nonlinear, like a linear or nonlinear function of x to lie in a certain length. There is some restriction. So you're restricting your x to lie on some curved or like linear space, problems arise. So, questions? Yes.
I don't really understand how T is sufficient in the sense that you could generate the same distribution.
Okay, a good point. So let's see how you can do it here. Okay. So first, let me ask, what is this distribution? This is a probability distribution. What is it? So can you describe? So we know that this is binomial. This is a probability distribution on like a random variable t. This is a probability distribution on a binary sequence. Okay. So can you describe what this probability distribution is? Who's saying that? Uniform. So what's your name? Just yes, yeah. I'm gonna ask your names to be able to know you. Jacob. Jacob. Okay, so Jacob. Why uniform? That's the correct answer. So it's uniform because whenever you plug in x, so either this holds or not. When it holds, the value is just this, which doesn't depend on x, right? And when it doesn't hold, it's just 0. Okay, so this is uniform, the sequence, all the set of all sequences whose sum is equal to t. Okay. Otherwise, this is not there. So what this is saying is, if you give me t, okay, which is like the count, how many ones there are, I can generate x, which has the same distribution by doing what? By going over the sequence, the set of all sequences of length n, whose sum is 4, just randomly pick one. Okay, randomly pick among all those, and the x that I get has the same distribution as my original x. Okay, so no matter what theta is, right? That's the thing. So the interesting thing is that maybe the original sequence was that, but remember that this is just one realization. Okay, so we have a distribution that's generating the sequence. What I'm saying is that I observe that this is 4. I give you the 4, you go and then just generate a random sequence uniformly among all sequences that have 4 elements. So the order might be wrong, but you know that that sequence will follow this distribution for whatever theta that this comes from. That's the interesting thing. Okay.
But it doesn't have to be. When you generate a sequence of theta, it could be not for us.
So here's the thing. So you generate, so you observe your data. It has a certain number of ones, right? So whatever that number is, that is sufficient. You have to have that. Okay. So you take whatever that is, it's 4, it's 5, whatever. And then you generate a sequence with the same number of ones. So this is saying that you have to do that. Right? This is saying take uniformly from the set of all x's whose p of x is equal to this 4. Once I have that sequence has the same distribution as my original data. That's what it's saying. Okay. So to like statistics is about like things happening frequently or in a large number. So just one sequence doesn't really matter. What this is saying is if you repeat this experiment many times, let's say you give me like many of these sequences. Each time I go calculate the sum and then generate by this procedure, that ensemble will have this distribution from whatever theta that original one was generated. That's the interesting thing. So maybe the original one was generated from like 0.2, like I give you like 1,000 sample of these vectors. Each time, in each case, you like there's a like sum difference. But for each one, you pick that sum and then you generate a random sequence based on that sum. The ensemble of the 1,000 sequences that you get has the same Bernoulli distribution. Right? Makes sense. You can try to convince yourself that it's going to be. Okay. Sounds good. Okay, so that's the sort of the meaning of sufficiency. Any questions? So if you do this procedure, let's say in principle, if you do this procedure, you can sort of prove in general some results like this. That if you have a family probability distributions dominated by a measure mu, again, this is saying that these will have densities little p theta of x, so it have p theta has density with respect to mu. All of them have the same underlying measure with respect to which they have density. A statistic is sufficient if and only if this density factorizes in this particular form. So that's a result called the factorization theorem or Fisher-Neyman theorem. And what this is saying is that the density factorizes into the product of two terms. One term, again, generally some h of x, the function of h of x that doesn't depend on theta, and one part that depends on theta, but depends on the observation just through the t of x. Okay, so the part of the distribution that depends on theta only depends on the data through this transformation of the data. Okay, so if you think about the Bernoulli example that we just did, this was like t of, remember we wrote it like this, 1 minus theta n minus t of x. You can just think of it as just, really this has one component, g theta of t of x. So the dependence on theta, the factor that depends on theta just depends on theta to g of theta. G of theta is like this function, theta t, 1 minus theta n minus t. Okay, so by this theorem, once you wrote this like that, then it's sort of obvious. Like immediately you can see that t of x should be sufficient. And it's like both ways, if and only if. In the discrete case, if you assume the density factorizes like this, then the procedure that we went through for the Bernoulli case, you can exactly go through to prove like probability that x is. So in the discrete case, these are all these are probability mass functions. So in the discrete case, this would be just the probability that x is equal to x. I can take the mu to be the counting measure, and this density just would be the PMF. And so what I do is, I'm saying that this probability distribution has a factorization, and so you go ahead and try to like compute this joint, which would be p theta of x is equal to x. This is like similar to what we did before, and then you plug in that factorized form, and then this t of x becomes t. So this was p theta of t of x. Under this is exactly the same as what we had before. And then you plug in t of x is equal to t, and then you sum over x, and then you divide. In the end, you'd show that the conditional distribution does not depend on theta. I let you do this for yourself. It's just exactly the same procedure that we did with this, but with a generic function here. Instead of this, you have g theta of t of x. Just repeat this argument, and then you prove that result. The converse is also quite straightforward. What if I know that t is sufficient? In the discrete case, we say, okay, so let's fix x and try to find this factor. Fix x, let t be t of x. Then I can write t of x, t theta of x as this. That indicator is vacuous because I deliberately set t equal to t of x. So this is equal to that, and then I can do condition. So this joint is like this probability of x given t times the probability of t equal to t. And this is going to be, I can take this to be g theta because it depends on theta and t. And this part by sufficiency does not depend on theta. So it's some t of x is equal to x. This is going to be h of x. And this holds for any x, so once you plug this little t in, you can see the factorization. So this was quick, but just do it for yourself as an argument. It's very simple in the discrete case. You just do the joint. Joint is like conditional times the marginal, and that's basically this form. In the general case, things are tricky because you don't have the same max. And it gets very convoluted. The proof is, if you look at classical book, it's very indirect, and some people try to make it straightforward. I'm not going to go into any of that. Just either accept this, or if you really want, go read, for example, like one of the more classical books, probably Layman's hypothesis testing book does it probably. It's hard to find actually the proof, measured theoretic proof. But they do prove something like this. Yes.
Sorry, the theorem box for mu.
Oh, right. Okay, so for mu, almost everywhere. This is almost everywhere. So these are again technical measured theoretic expression. It's like salt, or like salt and pepper. So once you have a result, you just throw it around. So it's just making sure that, so in measured theory, you don't have to have the statements hold everywhere. It's okay to be almost everywhere. So almost every statement that you say in measure theory is okay to hold almost everywhere. Almost everywhere means it could fail at like a set of x, but that set of x for which it fails has to have measure 0 underneath. So this is like saying mu of the set of x for which the identity fails has to be 0. In other words, this set has measure 0, or is a null set for me, which means that the complement has sort of full measure. We can't say measure 1 because this would be an infinite. But basically, the complement, like the way where it fails is 0. The measure is 0. For example, if we use the Lebesgue measure, any finite set has Lebesgue measure 0, so this would fail at a finite set of. Okay. And if again you measure theoretically inclined, and I'm not going to be measure theoretically inclined in this course too much. These densities are actually defined up to these measure 0 sets. So under Lebesgue measure, for example, this density is not defined everywhere. So you can just manipulate it at a certain set of points, still a valid density, because all you need is you want to integrate it against that measure over set. And then you integrate the finite set of points, that doesn't matter. Because of the way it's defined sort of up to manipulation on sets of measure 0. So that's where this comes from. For us, usually just think of it everywhere. Everywhere is fine. It's just to be precise, yes.
I was wondering if the dominated here means that the probability measure is absolutely continuous with regard to.
Yes, that's exactly it. So dominated means, if you want to be precise, means right. The family is dominated if dominated with respect to mu, if and only if, that's the definition. P theta is absolutely continuous with respect to mu. That's the notation. Okay. Absolutely continuous. So what does absolutely continuous mean? So yeah, what does it mean?
It means that if the mu measure is 0 in a set A, then the probability in this set will also be 0.
Yes. So for every event, or for every set A for which mu assigns measure 0, then P theta has to assign measure 0. So like if you want to intuitively think about, you can think of measures as it's like distribution of mass over the space, I think. I learned this, like at least this analogy from Steve Evans, probably at Berkeley, who learned from some of his advisors. So just piles of mass, measures a pile of mass on the floor, okay? One pile is like this, the other pile might be like this. And so the way that you think of it as, so these are the densities basically, so I think of, but really the piles of mass. And so the probability that you assign is like how much mass, or not just the measure assigned is how much mass there is on top. So the measure assigned to this is how much mass there is on top of it. According to this guy versus according to the other guy, it's this much mass. So it's okay. So it's this blue one. This how much mass is on top of this. That's the measure that the blue guy assigns to this. The other guy is assigns this much. Okay, assigns more than this. So now if the measure had like assigned like basically imagine like has support, which is the entire real line. Support means again where it puts mass. Then all this measure, for example, is absolutely continuous with respect to the other one, because sort of this sets like this assigned zero measure to are like these finite sets or like these weird sets, and this is going to be that. But for example, this thing. So suppose you have a measure which is like that, right? Assigns mass, positive mass here, zero else here. And the other one is like something like this, like that. Okay. None of these two guys is absolutely continuous with respect to the other, because, for example, there is a non-trivial set here. So this set gets assigned this mass by this guy, but zero mass by the other guy. Okay, so I can't say. So there is a set that the blue guy assigns zero mass to the red one. Assign a positive mass, and similarly, there is a set here that the blue guy assigns mass to the red one assigns zero mass. So these are not, none of which is absolutely continuous. So roughly speaking, the absolute continuity. So this is the formal definition, but it's saying that so wherever this guy wherever this guy puts mass, this guy has some mass. Okay. It's not like completely zero, and so I can have a density with respect to that. So I can integrate this guy. Basically, imagine I can integrate. I can translate this ratio to the like. There's a ratio of masses. I can translate what this measure does based on what this other guy does by multiplying by the ratio. So if this is like sort of mu of A, and this is like p theta of A, so sort of p theta of A divided by mu of A times mu of A gives me p theta of A. Because this is non-zero, for everything that this has non-zero, this is also non-zero. I can translate back into like the ratio. So this is going to be like our density. Imagine everything sort of shrinks. If this doesn't hold, then I don't have a density. I can't integrate. I can't integrate the density against this measure to do that. So this, if you think about this, and in the end turns out to be this is they write it like this. Then things become very small. This is going to be dp theta of x mu of x mu dx or something like that, or d mu x. D mu x, so that would be p theta of A. And they call this the Radon-Nikodym derivative, or just that density that we're looking at. Okay. So what you need is like, this has to be non-zero to be able to like translate the ratios. Okay. And so what we were saying is that there is some underlying measure such that all these parametric ones that they have, they might be shifted. So some might be here, some might be there. But everywhere that they go, put mass, this other underlying already has mass. So I can take the derivative with respect to that, basically calculate the ratios with respect to that, and then come up with a density that I can integrate against. So whenever I want to calculate the probability of an event under this, I'm going to integrate this density, which is just the ratio of the masses against this mu, and that gives me that. So if you make this formal, basically that definition sort of is equivalent to existence of these densities or Radon-Nikodym derivatives. So once you have that, that's the definition. Whenever I say dominated, like implicitly, I'm thinking of there exists a density. So this has a density so mu that I can integrate such that gives me probability. But really, the formal definition is that this part, the existence of the density, like this, and let's say if and only if p theta has a density with respect to mu, that's really a theorem, Radon-Nikodym theorem. I'm not sure if I'm pronouncing or like spelling Nico, something like that. Here. But they're sort of equivalent in a sense. So in any case, that's sort of a detour. Sounds good? Yes.
Another question.
Sure.
I didn't fully understand the factorization theorem, the first line, how the factoring.
Oh yeah, this one is by assumption. So we're here I'm proving the other side. To assume that t is sufficient, right? I'm gonna fix x. I'm gonna choose t to be equal to t of x. Okay, so if I have this, because of the way I chose this is really gonna have two holes. So this t of capital X is equal to little t, and this capital X is replacing the little x, because under this I can just replace the capital X with little x, right? And because I specifically chose t, this is lacking. In general, if I want to write it, it's something like this. Remember, you can write the joint as this times that, but this is true because I chose t specifically to satisfy it. So this goes away. Right? This is another mistake.
So that's the assumption.
That's the assumption because I'm starting with x. I don't have any little t. I just define little t to be that, and then in the end I plug in what this is. Yeah. That's where we define t here, right? Good. Any other questions? So that detour is not planned. So detour. Don't worry about this. It's like unplanned detour through measure theory. Measure. So any other questions? Okay, so let's see what is next. Okay, here's another example. Suppose we have x1 up to xn i from 0 to theta. This is going to be another one of our nice examples because this is sort of violates a bunch of assumptions, as you will see, and these interesting results. So this family is dominated by the Lebesgue measure. Any continuous distribution that you have seen is basically dominated by Lebesgue measure. So they all have densities, right? So this has, anyone knows what the density of uniform 0 theta is with respect to Lebesgue measure? Say p theta of x1 or xi. 1 over theta, yes. And then I usually put like an indicator to make sure. So x is in 0 to theta. Let's say if you want to integrate it against the entire Lebesgue measure, you're integrating from negative infinity to infinity, you just restrict the support. So it's only 1 over theta from 0 to theta, and then 0 elsewhere. So that's what it's saying. So we write it like that. Then the claim here is that the maximum of x1 up to xn is sufficient by factorization here. So let's see that. So the maximum is a valid statistic, so it just depends on the data. And that notation x subscript in parentheses n is the notation we're going to use for maximum. It's the last of the order statistics. I'm going to talk about order statistics. Like the first one is the minimum, x subscript 1 is the minimum, x subscript n is the maximum. So the joint density can be written as this product. So factor it's been by a genus. And then this I expand, I get 1 over k to the n. And this indicator, again, you know, you get a product of a bunch of indicators. And the product of indicators is the indicator of the intersection. So if I have product of a bunch of indicators, it's 1, then only all the components are 1. So this is going to be only 1 if all the xi are between 0 and 0, which is sort of obvious. You don't need the machinery with it. So that brings out the joint again. So it's going to be on the cube. And so in two-dimensional case, if you have 2 variables, it's just going to be 0 to theta here, 0 to theta here. It puts mass 1 over theta squared on this area and then 0 elsewhere. Right? So that's where the indicator is trying to restrict this. So then I can write the next line or the next equality, which is this indicator again can be written as a product of these two indicators. So I can say the maximum is less than or equal to theta, and the minimum is bigger than or equal to theta. Okay, so the product of these two indicators is equivalent to all of them being 0 to theta. Okay. So being 0 to theta, I just need to look at the maximum and the minimum. Once those are in the interval, then everything is good. And you can see the way that I wrote this is nicely factorized into a component which depends on theta, a component doesn't depend on theta. Right, so now I can call this h of x. And I can call this g theta of max xi, which is really our statistic. Okay, so that's our t of x. T of x is the maximum of xi's. Okay, so this part only depends on the data to maximum. So the part of the factor of the density that depends on data only depends on data tree this transformation. So by factorization theorem, maximum has to be sufficient. It's very easy, very straightforward. As long as you can write down the density and you can actually factorize it. Sounds good. So for example, the sum here may or may not be sufficient. You have to prove it. Turns out to be not sufficient. But the maximum is sufficient. Which is interesting. What it is saying is that if I have the maximum, now if I condition my data, the entire vector, on the maximum, the distribution does not depend on theta. And we'll come back to this later. The thing is, because we're in a continuous case, describing the conditional distribution is not that easy. It's not obvious. Like there's no closed form density to write for it, but you can describe that conditional density. It's worth thinking about. We'll come back to it at some point. I'll tell you. Especially in this case, suppose you have x1 and x2. Think about what is the joint distribution. What is the conditional? So let's say n is equal to 2. What is the conditional distribution of x1, x2 given, let's say max x1, x2 equal t. So if I fix the maximum to be t, now I condition on this, what is the joint distribution? This has to, if everything works out, if the factors of TM is true, this distribution has to lose the information about theta. There's no theta. And I'll let you think about what this is. Questions? I mean, I'll let you think about this offline. You don't have to think about it right now. It's not that obvious. Questions? Okay, let's do another example. Suppose the entire data. Oh, sorry. First, the entire data is sufficient always. Okay, so when I condition on the entire data, I can certainly generate the entire data, right, without the knowledge of theta. Or from factorization theorem is obvious. For IID data, there's always more reduction. There's always more reduction from the original data. And this you can see, I think it might be a homework problem. You write down the density. If I have IID data from its density, then the order statistic is always sufficient. So this is intuitively clear because the order in which the data come in doesn't have anything to do with theta because they're IID, I can permute them and it doesn't change the distribution. So the order statistic is formally the vector that contains the value in x1 of x and in a certain order. Like I can order them in increasing fashion. I call the smallest one x parentheses 1 and the largest one x parentheses n. Usually the middle guy is called the median, so on. The maximum, the minimum, and there's the second order statistic and so on. And so, for example, if I give you an IID sequence turns out to be like 1, -1, 2.1, 5, -4. That comes out like this. When I form the order statistic, I get -4, -1. What? 1, 2, 1, 5. And if I had the same data, let's say, but in a different order, the order statistic would be the same. Okay. I just the same values, but I reorder them in increasing fashion. If I haven't made a mistake. And so the idea is that by factorization here, or by intuition, you can say this is enough. I just need to know the values of it observed, not the order in which they came. And the way to regenerate it back is obvious. So once I have this, I just permute them randomly and I can get the original data. So that conditional distribution, you can imagine it's just a random permutation. So this, I think, is a simple homework example to prove. Just write down the PDF and look at it carefully. Just factorization theorem gives you that. Sounds good? So there's always a reduction. So if there's always a reduction, then the question is that how far can we reduce? Okay, whenever you can reduce, then the question is like a bottom line. And if there is, we would like to stop there. So you don't want to say, I'm going to stick with this. So just saying that I have a sufficient statistic is not good enough because the entire data is sufficient. The question is that can we say something is minimally sufficient? And it's really the next idea. So minimal sufficiency. So there is a hierarchy among sufficient statistics in terms of the data reduction. So intuitively, the order statistic has less information than the original one. And so we first have to formalize what this means. How do we measure reduction? Okay. Intuitively there is, so we want to make it precise. So once we make precise the reduction idea, then we can look for the minimal, the one with the smallest amount of information. So in order to make it formal, the interesting thing is that we can use a very familiar concept, which is the concept of functions, the mathematical idea of functions. Okay, so by now, probably too used to functions to realize there's something there. So there's some non-trivial in there, in the sense that functions really reduce information. Okay, So related there. So what is the definition of a function? Let's say you want to see. We can use functions as reduction mechanism. Anyone remember the formal definition of a function?
When x, the x only y.
There's only one. Okay, yes. So right. So that's like, I don't know where you learned this, but at some point you learn that the function formally is like if I have a function from a set, let's say x to y, say the set has like 3 things, and then this other set has a bunch of other things. So a function has to map every element to so at most one, usually exactly one. You can map it to 2 things, right? So that's the definition of the function. Everything in the domain has to go to one thing. And I'm also usually like people assume when they write it like this, everything in X goes somewhere. Some people like allow things to like not be mapped, but let's say everything in X has to go somewhere. This can go to the same thing, but it can go to 2 things. So you can't split one. So this can also go there, okay? But it can't happen that, for example, this goes to 2 things, okay? And if you look at this, you immediately see that this reduces information. So I had distinction between these 4 elements. Now I can distinguish only between this set of 1, 2, 3, and 1, 2, and 4, and 3. Okay, so once I look at the output of the function, this can be distinguished from this, but I can't distinguish between 1, 2, and 4 based on the value of the function because they're all the same value. Okay, so this function sort of loses information. Originally, you knew like these 4, but if I just give you what the f does on these 4, you can only tell me like either this happened or these 3 happened, but you can't tell me which of the 3 happened. Okay. So it's a fairly interesting notion of reduction. So there are functions that don't lose information. So what are they called? One-to-one, or like one-to-one is a bit it's like injective, they would say injective, or they can map basically different elements here to different elements. Or you can say one-to-one. There's also one-to-one correspondence, which means that everything here also has to get something. So injective is so injective is something like this. For things to be injective, I need to at least have that many points here. So 1, 2, 3, 4, 5. So this is, for example, injective. But it's not surjective because it means it's 1 half. It's surjective if everything here is gets something. And it's a bidirectional or one-to-one correspondence if it's both injective and surjective, at which case the 2 sides have to have the same result. But sort of these are terminologies. So injective, surjective, bijective or bijection, aka one-to-one correspondence. So I'm trusting that you know these things, maybe with different names. But the idea is that the general function need not be, for example, injective. If it's injective, it doesn't lose information. It's rejective. But in general, it loses information, then we can sort of use it for a definition. Okay. So what I'm going to define is I'm going to define an order among the statistics, which I write like this. So imagine the statistics are really functions of the data. So this is really T of X as a function. You can think of it. This is a S of X. So there are really functions. I'm going to say, for example, that S is larger than T if I can reduce S to T of Y at a function. So there is a function. If you can raise a function of S6. Okay. This is my own notation. It's not rather standard, but it helps I'll simplify. So this means there exists a function such that t is f of s. If I can find a function such that when I apply f to s, then I get t, then I write it that t has smaller, like less than t in the sense that has less information. But I roll s is like 100%. This is sufficient for the usual point by point. So really it's saying I apply s to x, and then if I apply f to this, then I really get t of x. Okay, so I can reconstruct t just from the information s of x. You can also write almost everywhere. T, so this doesn't have to hold everywhere again because x is going to be random. You just need this to hold the probability one under all of the probabilities in our family. So this almost everywhere. T is this identity has to hold. Not everywhere, but I'm usually ignoring this for the most part in that complication. So if this makes sense, then you have this lemma, which you can easily prove by factorization theorem, but should be intuitively clear that if T is sufficient, and I can reduce, we can obtain T by reduction from S, then S has to also be sufficient. In a sense, T has enough information, like all the information I need to estimate theta, and I can get it from something else by reduction, then S has to be sufficient. So this is saying whenever I have T less than S, and T is sufficient, it implies S has to be sufficient. You can formally prove it by factorization if you want, or maybe factorization, or yeah, maybe that's for that, or maybe from definition. I'm not going to prove it. So the idea is like, for example, if T is sufficient, then T the tree is like let's say T is real. If I raise it to the power of 3, this is going to be sufficient because this is invertible. It's an invertible map. I can get that T. But if T is sufficient, then T squared is not necessarily sufficient. Because if I have T squared, I can becomes back T. If T squared is sufficient, then T has to be sufficient. That's this notation. So T squared can be written as a function of T, so T squared is less than T. And so if this is sufficient, T has to be sufficient. Because I can always reconstruct this from T. So if T squared is enough, T has to be enough, because I can always get T squared from. Okay, so far so good. Right, so I have this notion of reduction, and it goes like, if this is sufficient, then implies that this is sufficient if this reduction holds. But I want to get to the bottom of this hierarchy. It's not clear that if S is sufficient, that T necessarily to be sufficient. It doesn't go the other way. If T is sufficient, then reduction might use enough information to make it viable. The other way holds. If this is sufficient, then anything above it has to be sufficient. So I want to go down now in this hierarchy and find the minimal sufficient steps. Okay, sounds good. Everyone on board. It's worth remembering this notion of functions here. So let's see. So what I want to show, again, it's not standard notation, but good to have. What I want to show first, define what is a minimal sufficient statistic. Intuitively, it's the one that achieves the greatest reduction. So T is minimal sufficient. So it's a minimal sufficient statistic if T is sufficient first. And T, whenever T is less than or equal to S, T is less than or equal to S for any other sufficient statistic. So any other sufficient statistic S that we can find can be reduced to T via a like functional transformation. So these two conditions, the first one means T is sufficient, the second one means minimum. So any other sufficient statistic that we pick, T is less than or equal to S in this reduction or this order. It's a very intuitive idea. Okay. So minimal sufficient statistics exist under mild conditions. And and sort of essentially unique modulo bijective maps. Maybe at some point we discuss this, or by the end you see why. But they're not trivial. So here's an example which I'll come back to. So x1 up to xn are dominant. If they dominate the family of densities that like dominate with respect to the Lebesgue measure, let's say. They have these densities where f is just some fixed density. So f, for example, could be this function, right? So if alpha is, so alpha, beta, and c are constants. C is going to make this the value of the density if you want. So if alpha is 2, this is just normal. Going to be normal with a certain variance, right? Could be this or could be like this, it doesn't matter. It's just 0 mean normal. That's alpha equal to 2. And alpha equal to 1 would be something like that, or something like this. It's just there is a kink at the origin. So it's called the double exponential Laplace. For some other alphas, you get the other things. So the thing is, if I have a location family, it's just the densities are translations of it. It's called location because the parameter is basically location of the sort of the mode. So it's a location family. Location family, the parameter tells you about the location of alpha. So if I have this, then in the case of alpha equal to 2, you get the normal family. It's not necessarily 1. Like, okay, could it depend, like this could depend, that could be the idea that this is normal space. But parameters say the normal theta and some variance. Then you can show that the summation of x's or equivalent the average is sufficient, but factorization theorem, this is easy. And then we'll show later that this is also minimum sufficient. So the mean, intuitively, if you have these, the mean is a good estimate of theta. Sufficiency is not necessarily about estimation, it's just about the information. So the summation, for example, is also sufficient, or the mean is sufficient. Intuitively, the summation of them has enough, like all the information you need. In the case of Laplace, there is no further reduction beyond the order. So the order statistic is minimal sufficient. We can't reduce it to something more compact. And so it's really dependent on the nature of the family. In this case, the particular notion of density, like it's not differentiable at this point. 0 causes this issue, or this interesting observation. That in a sense, like the Laplace family is more informative in a sense. Okay, so if you get a ensamples, so you have to have all the information there. In the Gaussian case, you can just drop everything. This just take the sum. Sum is enough. Okay, so we'll see how this works out. Any questions? Yeah.
I was wondering if the mean is always sufficient for a location family, or do we have a counting?
This is the counter example.
Okay, yeah.
Right. So it's a general location family. In the normal case, it's sufficient. In the Laplace case, it's not.
Okay.
Just in time for the counter example. Right. So, any other questions? So let me like try to develop some like machinery, try to prove this, but I'm sure this. And I'm going to use this terminology, which is again a mnemonic for short, DCS. So we're going to look at a family which is dominated. You now know what dominated means, but there's a Lebesgue measure underlying everything. And these guys have densities with respect to that. And we want the densities to have common supports. So support, again, I think I implicitly mentioned. So what is the support of the distribution? Or support of the density? Where the density is positive, or where the like this is the distribution is max. So these densities have common support. What I mean is that they I can find the set such that the location that they're positive just falls on that set for all of them. I don't have to vary theta sorry, it doesn't depend on theta. So an example where it's not common support is this. This guy. So you can see the density is here. The support of this you can say is 0 to theta. And it varies with theta. Okay, but the normal location family support is for each one of the members of the family, what is the support of the normal theta one? Yes, the entire real line, right? So they have common support. They all have the same support. It could be like a finite set, but it just, I can say that all of them are supported on this side. So the support is some sort of a minimal set on which the things are positive. Right? I can't say that the support of this is that. Right? It's like the smallest set I can find over which I have mass, let's say. There's a way of technically defining it, but intuitively you can see the support of it. Okay. The smallest, like let's say close set on which the density is positive. Again, the density is a little bit problematic because the density could like, you can violate it at a certain point. You can just redefine it to be 0 at like a fixed point, a finite set of points. But again, in the sense of measure theory, so we don't care about a finite set of points. So they have common support, so that family is gone. But basically I can restrict myself to this common support and be sure that all the densities are positive. So I can divide things by each other. Okay, so roughly, let's say for our purposes, roughly saying that there is a common set, let's say the support, such that t theta of x is positive on S, like for x in S and all theta, something like that. Okay, so once I restrict myself to this set S, then these densities are positive. Now I can divide things by each other and don't worry about division by 0. Okay. We'll come back at the end, talk about the case where things violate. Yes.
In that example right there, could you define again what the percent is?
Okay, so the order statistic. Anyone remembers the order statistic? Talked about this here. That's the definition. So when you look at the data, you order it in like the increasing fashion. This procedure gives you the statistic, which means that the order information includes the value in a certain point. That's called the order. Oh, it's perfectly yes. And so if you go back to this example, in the IAD case, the order of statistic is always sufficient. And we have an example in the Laplace family where there is no more reduction beyond this. So that's this. Good. Okay, so let's move on to this. Yeah, so this is saying because these are IID families, order statistic has to be minimal, has to be sufficient. This is saying that in this case it's also minimal. So there are cases where you don't have further reduction. Okay, that's that. Now, what do we do here? Questions? Yes.
I missed it, but what is DCS?
Yeah, so DCS dominated with common support. DCS. It's not standard terminology, just an abbreviation for me to not say dominant common support. Yeah.
The location is DCS.
Is it?
Yes.
It's a very good question. Is it?
What
Sorry?
is it not?
You tell me. Is it, so you guys tell me. Is the location family, it's a very good question. Is the location family always DCS?
I think when alpha is equal to 2, it is not DCS.
In this particular, okay, so we have to be like, so this is a particular location family.
Okay.
So the more general location family is F could be any density. So for these family, this family can mean this, it is DCS. Because the exponential F is 0. So these will have the entire real elements like and so on. But F could be anything. So for the general location family, F is any density. So can you think of a case where, give me an example of a location family which is not DCS? Uniform, uniform is a good example. So let's say F is just the density of, F is the density of, let's say -1 to 1, uniform on -1 to 1. Okay. Then what this is doing is going to shift this around, and the support is going to depend on it. So if this has not full support on the real line, then it's not going to happen. You see it, you're not going to have DCS now. This particular one, though, will have the same support. Any other questions? Okay, so restricting to this DCS family, what we want to show is the likelihood ratio function, in a sense, is minimal sufficient. So what is the likelihood ratio? Remember, the likelihood is when I look at these densities, divided with x, here's the function of k. So that's the likelihood. Likelihood ratio is like this relative some fixed point of the characteristic. So pick some theta naught, pick some theta. The likelihood ratio for these two parameters, keeping up not the range, that's the likelihood ratio basically for two parameters. When I'm going to look at it as a function, yeah, so if you look at this as I vary theta, I get a bunch of statistics. If I collect all of them, it's going to be a likelihood ratio, they call it the likelihood to process, whatever. That thing is still a function of x, so that function of x is minimal sufficient. So a little bit easier. Oh, actually, this is not easy. But let's say, okay, so let's say we're finitely many thetas. Because the parameter space is finite. That's the easy case to think about. Let's say, okay, theta 0, theta naught, theta 1, all the way to theta, let's say k. So I picked like one of them with, it doesn't matter which one. So I'm going to pick one of them and form these ratios. So x is random. P theta of x, theta of x divided by p theta naught of x. This is going to be a function of x. This is a particular statistic. And then I add p theta 2 of x divided p theta naught of x all the way to p theta of kf x divided by p theta naught of x. So this is going to be a vector. This is all that I can do. I can take the ratio of either one. Right? One of x divided by p theta 2 of x. But in the DCF family, I don't need to consider all the possible ratios. Because, for example, I need the other ratio, the p theta 1 of x divided by x, I can get the inverted this and multiplying like that. Right? So all the other ratios are constrained that way. There's no zero here. So the idea is that this is going to be minimal sufficient. This as a whole vector is a function of x. This function is minimal sufficient. Okay, it's a tricky idea, but it's like as statistical as it gets. So the likelihood ratio or the likelihood function, essentially the likelihood function, the shape of the likelihood function is minimal. So when I say likelihood function in the discrete case, the likelihood function is just a likelihood vector. In general, you look at this divided by p theta of x. As you vary theta, is just an entire function. So the theta maps to this. This is a function, like a functional form. That function also depends on x. So it's a random function. So that random function is minimal sufficient. So x maps to a function. So this mapping is not like a real number. It's just saying x maps to some of the elements. That's a function, but x maps to a function itself. That mapping is sufficient. Okay, x maps to likelihood ratio function. this mapping is sufficient. It takes a bit to wrap your head around this thing, but that's the idea, okay? It's easier in this case, in the discrete case, because that function is just a vector. You can say this is x. The map that maps x to this vector. Like a vector value the statistic. So this vector value the statistic is sufficient, minimal sufficient. So just the one line proof, and then I'm gonna do a little more. The proof, the idea is that point factorization theorem, once you look at the fixed theta and fixed theta naught, this ratio itself is gonna be a function of any other sufficient statistic. Once you write down the factorization theorem, if you pick a sufficient statistic, you can write down the factorization theorem for that sufficient statistic. And once you divide, you can see that this is going to be a function of that sufficient statistic. And because you can do factorization for any sufficient statistic, you can show that this is going to be a function of any other sufficient statistic. So this satisfies the second condition of minimal sufficiency. This is a function of any other sufficient statistic. The only issue is that if I just pick two data, this itself is not going to be sufficient. So the idea now is that I'm going to take more. You have this. Now I'm going to take another parameter and form this. This is going to also be a function of any minimal sufficiency. So this is going to keep stacking them. The idea is that once you stack all of these data, that thing becomes sufficient. So it's going to be sufficient and also a function of any statistic, so it's going to become linear. Okay, so that's the tricky part. That once I add all of these, then this thing is that's what we want to really show. This one, if we leave these, this one is sort of a little bit tricky. Okay, but then by the end, you have like a nice characterization of minimal sufficiency. Sounds good? Okay, we're out of time. Thank you guys, and see you next time.